All right, now we're talking about our first example of finding a tangent line to a curve given by an equation that we're going to have to implicitly derive. So what's really awesome about implicit differentiation is that even though we don't have y is equal to f of x for some function f of x, we can still find the slope at a given point if we are given enough information from an equation and a particular point that lives on the curve. So implicit differentiation gives us the means of doing this without knowing what y is technically. All we need to know is some x information and some y information provided by the one point that we are given. So that's how powerful this method is. Okay? All right, so we need to first derive this implicitly. Before we can find tangent lines, we need to find slope, right? So we need to find dy dx, which is going to be our slope of our tangent line. So that's our first goal. And looking at the equation, we need to derive this implicitly. So we first derive the first term, so we get 2x. The second term is going to require the product rule. So we add on, derive the first, so you get 1, leave the second alone, leave the first alone, derive the second. The derivative of y is y prime. Okay, put some parentheses around this third term here, this y, so it reminds us to use the chain rule. You take the 2, you bring it down, and then you subtract 1 from the exponent. So then you have plus 2, parentheses y, to the first, times the derivative of the inside of this. The derivative of y is y prime. And then finally, on the right-hand side, you have 3. Well, not 3. You're deriving it, so it becomes 0. Almost made a big critical mistake. There we go. So, again, the goal is to find dy dx. Always, always, always keep the goal in mind. So we want to get all of our y prime stuff on the left-hand side, and we want to get all of our non-y prime stuff on the right-hand side. So to do that, we're going to subtract our 2x and our y from both sides. Rewriting, this gives us xy prime plus 2y y prime, because we don't really need that exponent or these parentheses anymore. Anything to the first power is just that thing. And then this is equal to minus 2x minus y. Semi-final step, we have a y prime in common across all of our terms in the left-hand side, so we're going to factor that bad boy out, leaving us with x plus 2y. And that's going to be equal to 2 minus 2x minus y on the right-hand side. So then what we're going to do is divide both sides by the set of parentheses so we can get y prime by itself. So this gives us y prime is equal to minus 2x minus y all over this lovely parentheses. Okay, and that's that. All right, so we have our y prime. This is our equal to dy dx, and also equal to the slope of our tangent line. So even though we don't technically know what our y function is, we do know what its derivative is, provided we have enough information to plug into both of our x and our y. So that is, if we're given a point on our graph, an x and a y point, we can find the slope at that point. Turns out, at the very beginning of this problem, we were given a point. We were given an x value and a y value. So in order to figure out what this m is, we're going to substitute in x is equal to 1 and y is equal to 1. So every place you see an x, you replace it with a 1. So writing out what we mean here, so we have y prime at 1, 1 is equal to, I tend to be more verbal in my mathematics than symbolic. I'm going to simply plug in 1 for x. So I have 2 times 1 minus 1 for y, because that's what we're plugging in. We have, this is our x, this is our y. And then all over 1 plus 2 times 1. So this is our m. And this is going to be equal to, okay, simplify a little bit. So we minus 2 minus 1 over 3. Well, conveniently, this is going to be minus 3 over 3, or just equal to minus 1. So since we had that point given to us, we were able to find the slope of the graph at that point without ever knowing what y is equal to. Okay? We just needed enough information at one point to pull this off. All right, so we have the slope of our tangent line. Now we need to find the equation of our tangent line. So we need point slope form. This is always my go-to when trying to find tangent lines, which is going to be the equation y minus y0 is equal to m times x minus x0, where your x0 and y0 are a point that live on your line. We were given that. We are given a point on our line, a point on our line, 1 and 1 for our x's and our y's, because at that point on our graph, this tangent line is going to touch that. So we know that this is a point that's on the line and on the graph. Our m is equal to minus 1. So plugging in all relevant information into this equation, we have y minus 1 is equal to minus 1 times x minus 1. FOIL a little bit, so we have y minus 1 is equal to minus x plus 1, because I just distributed, that's all I did there. And then finally, I'm going to add 1 to both sides. So I have a y is equal to mx plus b type formula. So I have y is equal to minus x plus 2. This is your final answer. This line, y is equal to minus x plus 2, is going to touch at exactly the point 1, 1 on our graph. And we were able to find this without ever knowing what our function y was equal to. The power of implicit differentiation at your fingertips. So give the next example a try before checking out the video. It will work basically the same way as this example. It's going to require a little bit more use of fractions and radicals, but it's not too terribly challenging if your algebra is on point. So with that, we'll wrap up example 1.